Hello, happy day 167. We're right there, getting up on the end. We've got this week of school, and then next week, there's a couple days of regular classes, and then the final exam. Grades are due on the 10th, and the last day of school is the 12th. Why the grades aren't due on the 12th on the last day of school? Beyond me. So it goes. Okay. Before the year is out, I'm going to show you how to build a motor out of magnets, wire, and a battery. So that's the essential question that's going to run through these these last few days of class. Let's see. So, some goals. In order to understand how to do this task, you need to know something about electricity, right? How it flows. You need to know about how that energy gets from one place to another. So you need to understand electric fields. And then you also need to understand something about magnets. So there's those big things that we're trying to nail down in these last few days of school. Pretty cool stuff. So, 4 goals for today that you're able to conceptually, all right, so this is like the theory of it, ascertain and numerically, so it's the math, calculate the properties of an electric field by testing the effects of a charge and distance on the strength of an electric field and force. So, basically, what this goal means is like if you had a couple of say electric fields, a couple of big charges, and then you put something in the middle, how would it move? Think of like two magnets, and you put a piece of metal in the middle. Where's it going to go? Is it going to go to one magnet, go to the other? Is it going to move around in a path? What's it going to do? Next, we're going to play something called electric field hockey for you to build on this skill. And so I'm going to have you align positive and negative charges so that a positive test charge will enter the goal. We're going to learn how to interpret electric field line drawings and define something called resistance and Ohm's law. Resistance is something that you use if you use a electric stove. If you use something that heats up water, like in your dishwasher, or maybe you have a steamer for the floor or for your clothes, those all have a resistance element that gets hot because it's hard for energy to flow through them. Lots of things like that. Okay, so warm up. Give it a shot. If you want some help, you can click on this link and go to slide 2. Try it. Come on back. Okay. Excuse me. So, a while back, maybe it was even last semester, we talked about different kinds of forces, contact forces and non-contact, aka field forces. And we're finally getting to the second of our field forces. The first one was gravity. And so just like gravity, there's the electric force, which is a non-contact force. You can see here that there's a charged balloon. Somebody rubbed it on their head, and it is approaching a electroscope. It's a very small thing. It's got a needle on it, and that needle follows the path of the electric field. And when this gets close with its negative charge, it deflects or repels a negative charge here on the electroscope, causing it to move. So, some things that we know here. Well, electric force is a non-contact force, and electric field. So, all charged objects make an electric field that extends outward into the space that it surrounds. Charged things can attract or repel at a distance. And there's a stinky diaper analogy, and basically it goes like this. So, if I took a stinky diaper, all right, full of, say, poop, and I took it and I put it over there in the corner of the room, would it smell here where I am? Well, that's about 3 meters or 10 feet away. Well, probably. Let's say that the diaper wasn't very stinky. Just a teeny little bit of poop. It didn't smell that bad. It probably wouldn't smell that bad over here, right? Because it's not that strong over there. And by the time it gets to me, it's just so spread out that it's not that bad. If it was a horribly stinky diaper, kid ate something really bad, then it would definitely smell bad over here, because if it's strong over there, it's, even though it's spread out by the time it gets to me, right? We're spreading as we get further apart. It's still going to be strong enough, that force, that smell. It's like the force. Now, what if I got farther away? Smells worse or smells better? Smells worse, right? Because the further away you get, the more things spread out. And the closer I get, the opposite would happen. So that's this. One stinky diaper will fill up I forget what goes here. Oops. I'm spacing on the word that goes here, but if you stick your nose close to a stinky diaper, the smell will be quite strong. The farther you get from the diaper, or the farther from the diaper you get in the room, the less smelly the scent gets. However, there will always be at least some like hint of stinky diaper everywhere in a room. Maybe this is closed room. I forget. Anyway, you get the idea, I hope. Intensity, that's what we're talking about here. The closer to a charge, or the higher the charge at the source, the stronger the field. And we've got a test charge. A test charge, again, is something that you would put in the field, and you would see how it behaves, and that tells you what the field is. So that's the charge used to measure the electric field strength or intensity. And so there you go. Okay, we're going to do a few things today. They're all kind of short. We got an electric field hockey pre-lab. So the link for that is here. There we go. We'll let this load. So I used to give this, I used to print this out and cut it in half. So it's the same thing top and bottom. You just got to do half of it. Okay, so we're reviewing some vectors. We studied vectors back when we did kinematics, and the idea here is that electric fields around multiple charges add vectorally. That means if they have the same direction, then they add to each other. If they have opposite directions, they subtract from each other. And then if they're at angles, then you actually have to add the angles together to get the resultant. So some examples. Here's a dark one and then a light one, and they're both in the same direction. So we're going to add or subtract. We're going to add, and you would add the length of this one, the length of the light one, and you get this one that's, the sum of both of them. Here we've got a short to the right, a longer to the left. They're opposing, so you'd subtract them, and basically you get a short to the left. That's the result of these two things. Here we've got to the right, short to the right, and longer up. And so you're going to get something that's a little bit more up than right, and that's the resultant. So do the same thing here, right? Draw these and then add what, or say what the result would be. And then here, think about the space around a charged object and how that space gets affected. So I'll give you a few minutes to do that. Go ahead and pause the video now, and then I'll go over the answers. Okay, are you ready? So for number 2, the space around a charged object is affected by the charged object. The space surrounding the charged object is described as an electric field. For number 3, the electric force vectors or force vectors around multiple charges add vectorally. A negative charge and a positive, well, those are opposite, so opposites repel or attract. They attract. For number 5, a negative and a negative would repel. For number 6, the strength of the electric field surrounding a charged particle depends on the proximity of both particles, or the distance between them. I'm sorry, I got that backwards. On the strength of both particles and the distance away from the particle. That's the proximity part. Okay, and number 7, if this positively charged object, this right here, was allowed to move freely, but the negatively charged ones couldn't, so these are fixed and this can move, what's going to happen? So, these are opposite, so attract or repel. Attract. So this positive charge is going to try and move towards this one, and then the far one. The one it's going to be the most attracted to is the one that's closest to it, since they're all the same charges. So that means it's going to be most attracted to this one. And so it would aim a little bit more towards that first. However, it can't get there. It's going to bump into this. So my dashed line would go dash, 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 hit here, crawl up the wall, and then I would go directly to here, probably on the bottom side. And then my guess is it would either wiggle its way through here and end up in the middle, or it could even swing around and just stay right here. It might be so strong, the attraction to this one, that it never actually ends up over here in the middle. Okay, so that's the idea there. Let's move on. So we've got some electric field notes, slides 2, 7, and 8. So we already looked at slide 2. Talked about that. Let's go to slide 7. If you want an advanced treatment here, then you can take a look actually at a couple of things. One, there's a video that covers all of this. It's right here, and it's a crash course video. Crash course is put on by PBS. They got this video on electric fields. It's pretty good. I chose to watch it at 0.75 speed, and if you don't know how to do that, you go to this little settings thing and choose playback speed. And the reason for that is crash course videos, all of them, they go really fast.
So we want to describe complex situations involving charged particles using more than just Coulomb's law. If we have an object with a known amount of net charge, can we predict how other electric charges will react when they pass nearby? Well, British scientist Michael Faraday came up with a way to do just that. He hypothesized
that he did.
Field line signifies the magnitude of the electric force on small q, and the closer small q is.
Sorry, I pushed the wrong pause button. So this video talks about the equations that we use and also which way the charges function. It also explains the idea of a test charge, and so is really great for that. So moving on, the slideshow that I've provided also does that same thing. It talks about the equation for electric field strength, which is the force divided by the test charge. Here's an example. We've got two charges, big Q and little q. They're a distance apart. There's a force, and based on that force and these two charges, we can figure out the electric field. And the math for that looks like this. You plug in Coulomb's equation for the force, and you get a simpler equation for the electric field that depends on a constant, that depends on the charge, the source charge, and the distance between the test charge and the source charge. So let's look at this example. We've got a balloon that's charged negatively. We've got another balloon that exerts a repulsive force on balloon A. Which way is the electric field vector created by balloon B? Is it going to be towards balloon B or away? And let's see. So if it's negative, then it's going to be. I think we actually had that in the video, didn't we? All right. So positive charge away, negative charge in. Oops. Since they both have the same charge, they're going to repel each other. And there you go. Okay, moving along. Some practice. I went out of order. Sorry about that. So I wanted you to play around a little bit first with this electric field hockey activity and then take the notes. Oops. Let's take a look at the field hockey game. It's pretty cool. Okay, so instructions for this. Basically, what I want you to do is just sketch what you see and sketch what's going on. So you're going to open up this simulation, and then you're going to draw the starting location of the puck, where the goals are, and any obstructions, um, and then the location and sign of all the charges, and some of the electric field arrows. So again, just like you saw here, you're going to draw some of these. And so let's play one together. Oop, there we go. You can make this full screen when you get it open. I won't. Do do do. Really exciting today. While we're waiting, I got the internet service today. Technician came out, replaced some wires, cleaned up some stuff on the telephone pole. It was exciting. Looks like this is frozen. Go ahead and pause it for now and get it to work out. Okay, great. Well, as soon as I paused it, it was ready. So here is the most basic level. You can choose your level here. So how would you get this positive test charge to get in here? Well, let's see. You can try to add a positive. You can see what that positive is going to do. It's going to push away. You could try that. Hey, amazing. And so I can click the screen. I could also have added a negative. By the way, I'm clicking and dragging this around. Put a negative back here. So you see these lines. This shows the darkness of it shows the strength, right? So the closer you are, the stronger it is. I could add more. And you'll see that they start to get darker further away because the field is getting stronger. And you can see that the arrows are pointing towards the negatives. So if I was going to draw this, I would draw the goal, the puck, and the charges, and I would draw a few of these lines going towards them. Maybe like one here, one there, and one there. Takes 15 seconds. There you go, and ta-da. Okay, there are other levels, right? Like it gets hard like this. And so you have to figure out some way to get around this, right? And so, that could be that you attract to here, and then you try to do something to get it to go around. But this brings in all kinds of issues. Like, how do you get it to, see, it came back. It was like in orbit. So how do you deal with that? Some of these are easier, some of them are harder. Don't get too hung up on one. Again, the general idea is to understand that positive charges repel and negatives attract, and this is just a fun way to try these out. And this one's extra great. It comes with charges on here and the moving object, but it's a fun challenge. So try those out. There's 9 levels. Okay, so far we're through 1, 2, and 3. Let's talk about electric field practice. So, where's that? There we go. Okay. So, which drawing shows the field around a positive charge? So remember, a positive charge, does it go in or out. You can refer back to the slideshow or go back to the video, but the answer is out. So that would be A, which shows the field around a negative charge. B, which shows an attraction. So an attraction would be opposite charges, right? One positive, one negative. So, well, here's a positive and here's a negative. So that's C. And which shows a repulsion. Well, there you go. All right. This is why when you have two magnets, you're trying to force them together, and it's North Pole to North Pole, and they won't. This is the repulsion force right here. They don't want to be together. These lines aren't allowed to cross. So the closer you get, the more these lines have to bend vertically because they're not allowed to cross. And so the closer you push, the harder it gets because those lines are really having to bend, and they don't want to do that. All right, so cool. If you did that before I talked about it, nice. If not, then try doing the rest of these and then come back and we'll go over it. Okay, so in drawing F, E? Yeah, drawing E. Sorry, this says F. It should say E. I think I can fix it. Ta-da! There we go. In drawing E, a positive test charge is placed at location X and then at location Y. Compare the force that it experiences at X with Y. So at X, what's it going to feel? It's positive. What's this? This is also positive. So it's going to feel attraction or repulsion. Repulsion. And what about when it's here? Also repulsion. So it's going to be repulsion at both spots because they are like charges and so they repel. And so then the next question is it going to be a strong repulsive force or a weak one? And well, that force depends on the strength of the charges and also their proximity. Since the charges don't change, it's the same charge. The only thing that is changing is the distance. This one's a lot closer, very strong. This one's farther, weaker. If you had a positive test charge at X and let it go, what would happen? Well, think of the field hockey that you've done by now. It would just zoom straight away from this center spot. And that's because like charges repel. If you held the positive test charge at Y and let it go, what would happen? Well, what would it do? It would do the same thing. It would just move away from the center. The only difference, would it go faster, slower, or the same acceleration? It would accelerate slower, right? It would be moving like this, and then it would speed up and speed up and speed up. Versus this one, which would start off slow, but then move a lot faster, quicker, because it would experience a stronger force. Okay, looking at drawing E, how would your answers change if the source of the electric field were negative? So, if this was negative and this was positive, then it would be attracted, right? And very strongly attracted. It would just kind of go like this, little orbit around here. This would be less strongly attracted, but it would move towards it just the same. And again, do this kind of orbit thing. How do electric field lines show you the strongest point on the electric field? Well, so the closer they are together, the stronger the field is. And so if you look here, right, if we were to draw a circle right here, you would see that each of these lines is very close together. These two, they're all very close together when you get near the center. But out here, look how far apart they are, right? I can fit my whole little plus sign multiple times. 1, 2, 3, 4 times there. Here I can barely fit it once. So much stronger here, much weaker out here. And that's it for the practice. Wrapping up, which way would electric field arrows point around a negative charged particle? These are all questions for you to just try and answer right now. If you can answer these cold without looking at any notes, then you are in good shape. So if you haven't done that yet, do it. Okay. Negative charged particle in. And that's the secret for remembering it. Negative in. There is no fancy thing for positive out. Positive pout. I don't know. But negative in. All right. They both start with the same thing. In. I know it's in, but the same sound. So, negative in. How can you get a charged particle to change direction? Well, apply a force to it. You can attract it or repel it with a negative or positive charge. When electric field lines are drawn close together, what does that tell you about their strength? Stronger. All right, tomorrow we're going to look at resistance and Ohm's law. And so we're also going to talk about voltage and current. And so voltage, current, resistance, we're going to talk about those three things. And so there's some reading on that and a little document for you to do the reading. Let's go through the reading real quick, just to see what's in here and go over a few of these things. Okay, we got it all loaded. So just talking about voltage and current a little bit right here. So the idea of voltage and current. Voltage you could think of as pressure. Pressure in a hose is a good way of thinking about it. The harder you push on what's in that hose, the higher the pressure is. All right, and we think of that as voltage. Right, that's what voltage is. A higher voltage battery pushes harder. And then there's current, and that's how much can flow, right? The amount that can flow. And so a little hose like this can only flow so much. A big fire hose like this can flow more. A giant pipe can flow more current. There's resistance to flow. And so that's what this is all about. Resistance is important. You can use resistance to make a wire get hot. Also, if you want energy to flow, you want low resistance because you don't want to waste energy on heating up wires that are going from a power plant to your house. You want as much of that energy to get to your house as possible for environmental reasons, but also mostly for monetary reasons, because if you waste it, the electric company doesn't get paid for it. So there's some information about thick wires versus thin wires and wires at low temperatures. And here's a picture of a resistor. This is what resistance looks like on a wiring diagram or a circuit diagram. This is all about Ohm's law, which is related to current and voltage. And these are all pictures of resistors. They're small. All right, they are pretty small. And they all have different values. And the value of the resistor is actually denoted by the color and number of these little paint marks that are on here. So there's some questions about resistance. There's a question about electric frying pan and resistance in a lamp. All right, so in an incandescent light bulb that has the little filament that goes across, that thing is a resistor. It resists flow, and in doing so, it gets so hot that it emits light. What about shock? Well, so we want to think about shock. One, for safety. Two, because sometimes it's useful. Some people use shock to exercise their muscles. But more often we think about shocking to restart the heart. So there's some questions about that in here. And also, if you ever wondered why this is possible, for a bird to be on a wire and not get shocked, why it is that there are 3 prongs on some plugs but not others. It talks about it. So that's it. All of the prompts for this, they're all here in the guided reading. And that's it. All right. So enjoy.